I said u was natural log of x to the 12th. And I tried just x to the 12th to begin with, but there was no way to get the natural log. So I said u is natural log of x to the 12th. Then du is 1 over x to the 12th times the derivative of the x to the 12th, and the derivative of x to the 12th is 12x to the 11th. And I didn't realize until that moment, oh, that's just going to be 12 over x, and I have the x.
Miss Miles, this isn't fun. This isn't fair.
So 1 over natural log of x to the 12th, the derivative is 12 over x dx, and all I need to make that equivalent to the line above it is that coefficient of 1/12. Now that's how I did it. It's not funny because now it makes sense.
It's funny because I spent like 20 minutes on this problem.
Yeah, it was the hard one.
I got 1 point for it, and it's just like 2 steps.
It's in choosing the right u. But let me show you what Emma did, because it was interesting. Miss Emma said, if I have natural log of x to a power, I can bring the power out front. And that's even cooler, because you can bring that, dx, you can bring that 1/12 out front and have 1 over x natural log of x dx, and then u is just natural log of x, and du is 1 over x dx. So there's your same 1/12 that I got right there, and I don't remember if you had this scribbled out to the side, but somebody wrote, integral of natural log of x, question mark? Was that you? Think of it as u. What's the antiderivative of 1 over u? Natural log of u? Oh, it's just natural log. Oops, it's natural log of natural log. Does that make sense, Miss Michaela? All right. I never said it was pretty.
I never want to see this again.
Well, you will, so don't be that way. All right, so 7.2 will be we'll get to review stuff that you told me yesterday. I wiped 7.1 out of my head completely. I don't remember how to find area at all. You'll get it back from today when we start volume. And I put some cool videos, even more. I put some more on YouTube yesterday. I don't know that I'm going to spend class time, maybe just 1 minute. I want to show you something, but I want to get started on this and then see if a video that I found last night helps you at all. I brought with me the first page of 7.2 just to say, yes, solids of revolution exist in real life. A lot of things that have symmetry, come from rotating something about either the x or the y axis. And when I looked at these problems last night, I had a really hard time imagining the function which would rotate around the x-axis to give you that shape. That's an axle. I can imagine this one because if that's the y-axis and I had this function right here, spinning it around and around the y-axis would generate that funnel. No, the whole funnel. If I just have this shape and spin it around and around the y-axis, it makes that funnel. And I could see it for the bottle. For the bottle, if I have, let's play like, I don't know exactly what function it would be, but like I could draw or just follow a line would be fine. If I had that shape and spun it around the y-axis, it would generate that bottle. So things with symmetry like that are often solids of revolution or something similar. I just want to show you that they exist. And now let's figure out how to determine the solid of a revolution. We're solid of revolution. We're going to build up to it slowly. All right. What's the area of that rectangle? That's L. That's L. And that's R. Oh, you don't have the notes. Oh, you needed the notes today. Gosh darn it. Okay. All right. You'll just, look on and then make a copy of it after. The area of that rectangle is length times width, which is the width with R. Don't know why. Maybe I'll know why in a few minutes. But area is length times width. And what solid of revolution would be formed if that rectangle was spun around the x-axis? Yeah. Now, this was one of my greatest weaknesses in Cal 2. I can't spin something around in my head, but I can draw the rectangle and then the mirror image of the rectangle. Just flip that rectangle over, put it below the x-axis, and then I can imagine a spinning motion within that. As I spun it around and around the x-axis, it would become that cylinder. Yeah. So what would, let's answer with this. It's a cylinder. So what would the volume of that cylinder be? If this radius of the cylinder is still R, and the length of the cylinder is still L, what's the area of this circle right here with radius R? Pi r squared is the area of that circle, so what's the volume of the cylinder? Pi r squared L. Now that's as complicated as the geometry is going to get, Miss Cheryl. You don't have to worry about it. If you know that the volume of a solid is the kind of the area of the end times the length, that's always true. All right? So let's move away from this nice geometric shape that we already knew the formula for and see how to apply the same thing to something that's not linear or not a geometric figure that we know the area for. How do we find the area, this is 7.1, how do we find the area bounded by this curve? This curve is 1/2 x squared from the x-axis, from x equals 0, the origin, to x equals 4, right there. How do we find this area? All right, integral from 0 to 4 of 1/2 x squared dx. So what would that look like if I spun it around the x-axis? It would. It would. I would have the same function here. And I can draw its mirror image reflected with respect to the x-axis. And then I know the spinning would be this. I'm having a pretty good funnel then. Wish I had a funnel cake. I should do that. I should do that the day. Yeah. Okay. So, here's the area under the curve. This height is still x equals 4, and then, well, let's say in general, any point on that curve. Any point on that curve is some x and then f of x, right? So I can imagine this funnel being built by a bunch of little rectangles that are getting taller and taller, but the height of each rectangle is f of x. Whatever f of x is at that x. So this is still 1/2 x squared is this radius. How would I find the area of that circle? Yes, the radius. Let me write that. The radius is 1/2 x squared. So how do I find the area of that circle on the end? Okay, so pi times 1/2 x squared, because that's the radius. And then what, that would just be this particular circle. How do I add up all the other little circles inside? That's what the integration does. Each of these x's, there's a little disc. Instead of just being a rectangle, these are really discs. And the area of each disc is pi times this r squared. So if I want to add up the area of all those discs, that's what integration does. Add up all the area from x equals 0 to x equals 4 of the radius squared dx. Because it's the height, just like here, the radius was the height of that rectangle, and the height of that rectangle was constant, which is what made it a rectangle. The height of these rectangles, or these discs, are not constant, but they're all given by the function, whatever 1/2 x squared is at each x. All right? So what that does is, I'm going to write it the way I wrote it last night because it makes sense. The radius is 1/2 x squared, and so this is pi times the integral of r squared dx, and that adds up the areas of n, make sure I see that, n discs with a surface area pi times r squared. Each disc has a surface area of pi times 1/2 x squared, and then you multiply that times the length of the interval, which is integrating from 0 to 4, and that gives you the volume of that solid. I need to change these. Adds up the volume of end disk with a surface area of that and width of dx. The height is given by the function. The width is each little disk has a width of dx. All right. So far, so good? So far, so good. All right. Let's generalize it. In general, if we had some function r of x, every point on that curve is an x and an r of x. We're going to imagine infinitely many rectangles. Look up just a second. If my pen is two-dimensional rectangle right there, at the x-axis on this particular graph, the rectangle would be the tallest. And as I built rectangles moving to the left, the rectangles would become shorter and shorter. But I can imagine infinitely many rectangles sliding along under that curve. Each one would have a height of r of x. Yes? All right. So if I spun that around the x-axis, what shape would that make? It'd make a hemisphere. So the volume would be pi times the radius squared. Pi times the radius comes from r of x. Where do I need to integrate from? As these rectangles slide along, they slide along from A to B. So pi times the integral from A to B of radius squared dx. Oh, yes, tell me over. I'm writing out of sight. That kind of makes sense in some way that it didn't make sense to me the first time I saw it. If y'all are nodding and understanding, I'm tickled for you, but the first time I saw that, I didn't get it. It's just the same as this. I understand the area of a rectangle. I understand the only difference between area and volume is you multiply, this is the surface area. The surface area times the length is how we find volume. So applying that to a curve, the surface area is still pi times the radius squared, only the radius is changing now, which makes it calculus instead of algebra. F of x gives the height of the rectangle at each point, or since this is not a rectangle, really we're thinking of these as being discs. And the height of each disc is 1/2 x squared. So that's the radius. Pi times the radius squared, added up from 0 to 4, will give you the volume of that curve. And the same thing here. All right. What if we were rotating the function with respect to the y-axis? Because not everything rotates this way. Some things rotate this way. Well, wouldn't it be? Yeah. It's just this. Okay. Well, that's what it looks like. So if we were rotating with respect to the y-axis, and pay attention to these little arrows that tell you which way the function is being spun, being rotated. This is around the x-axis and this is around the y-axis. It makes sense if I'm spinning with respect to the y-axis, then I would be adding up horizontal rectangles or horizontal discs. This is the width of each disc is delta y. And since I'm spinning horizontally, look up just a second, watch my pen. The bottom rectangle would be the tallest, or maybe we should say widest. And as we go up, each rectangle is shorter, but its length is still determined by the function, which is now a function of y. So the integral that gives you the area, the volume of that cylinder is still pi times the radius squared. The radius squared is a function of y. dy integrated from where to where? Yeah, C to D.
Why do we say like dy instead of delta y?
Remember the differential? dy is an approximation of delta y. dx is an approximation of delta x. When we're integrating, we just write the differential. All right. So I want to add two things to these notes right here. When we're rotating with respect to the x-axis or any horizontal axis of revolution, then make sure you realize that you're let me write this. I'm going to write it just like I wrote it last night. The bounds of integration whenever you see WRT, that's a mathematician shortcut for with respect to x. My bounds of integration are x values because I'm integrating a function in terms of x and my integration is with respect to x. When I'm rotating something around a horizontal axis, I need everything in terms of x. The limits of the bounds of integration are going to be x values. The function has to be with respect to x, and my integrations with respect to x. So you can write the same thing in terms of y for that second integral. If we're integrating around a vertical axis, then my bounds of integration have to be with respect to y. My function has to be in terms of y. Which means instead of y equals x squared, it'll be x equals y squared. And then I integrate with respect to life. And the thing that I notice about both of these is that my rectangles are perpendicular to the axis of revolution. If I am integrating around, or if I'm rotating around a horizontal axis, then I have vertical rectangles. And look up at my pen just a second. I'm imagining those discs moving this way, getting shorter and shorter. If I'm rotating around a vertical axis, I imagine these discs, my rectangles are horizontal, and I imagine these discs moving from the bottom to top, getting shorter to shorter. And when I started thinking of that last night, how many of you have seen a lathe? You know what a lathe is? A woodworking tool? Well, not just woodworking, but metalworking, everything. Have you seen one, Sam? A lathe? Have you seen, like, on how it's made? Have you ever seen a baseball bat being made?
No.
Okay. It's integration. And it's everywhere.
Mary and I always tell me that when she always sees calculus, unless she can't not see it, she sees it everywhere.
Suddenly that reminded me of Sixth Sense. I see dead people. It's like, I see calculus. I really do. Everywhere.
That's another shirt.
It would have to have the voice. Somehow you have to make that that shirt whisper. I see calculus. That's a scary movie. I don't want to see somebody whispering that in a movie. All right. Nobody has seen a horizontal lathe. Thinking of that. Oh, sorry. Wasn't that loud at home? Okay, look at this. Imagine these horizontal discs that, I'll stop it at the perfect point to show you the function. Isn't that the coolest machine ever? It's churning, it's doing calculus. It's churning out a baseball bat. And I thought it was going to project on the board so that I could draw something, but then I realized, no, I'll be drawing on the TV. I don't want to do that. Let me stop it at the perfect moment here. I don't care about the back. This video is actually a promo for that machine. It's not anything to do with calculus, but because I've seen a lathe turn wood before. You know, fancy table legs, they're made by a lathe, which is doing calculus. No, the person who built it is really smart. Machines aren't smart. The people who built them are smart. Okay. I wish this was horizontal, but imagine this is your x-axis going right through there, and this is the function approaching the x-axis as that is spinning at different heights determined by that function right here. You get the wide end of the bat, and then the narrow neck of the bat, and the taller ball hitting part of the bat. There may be a different name for that. I don't know. But do you see calculus?
No, I do.
Like discs of various heights moving this way as the bat spins around. It's this curve right here that determines the height of the bat at each point. It is kind of cool. Yes, ma'am.
So then does it matter that those are underneath the x-axis, like when you're taking the angle? Because sometimes it matters and sometimes it doesn't.
Okay, I see what you're saying. Let me think of the best way to answer that. Best way to answer that is this area. Let me just hold this up. This area, the curve is above the x-axis. And so the circumference, go back to the rectangle, the circumference of this is just the radius times, no, it's the radius squared times pi. That radius is positive. You're just finding the area of one rectangle, and then you're spinning that rectangle. So you're finding this bat would consist of infinitely, think of different size coins that you could stack up, starting with maybe a nickel, and then going to a dime, and then getting back to a nickel, and then getting up to a quarter. You see what I'm saying? The area is just determined by the radius, and the radius is above the x-axis. I mean, we would have a problem if part of the radius was below the x-axis. I think I have an example like that.
Yeah, how do you do it? Like, what do you do with like cosine or something? What does that look like when you're spinning a bunch?
That's interesting.
Like a weird slinky.
Yeah. Yeah. I really like that, and I think it would help y'all. I know it would help me. I mean, because the internet wasn't invented when I was in school. My teacher had no way of demonstrating this, short of bringing in a lathe, but I can show y'all so easily now. Here's something fancier. Look at the block of wood. And then there's the discs. That piece of metal right there is the axis along which the function is spinning, and the function would be that. That's the first sign of excitement I've seen, by the way. I keep looking at somebody to go, that's amazing!
I'm sorry, I didn't get much sleep.
It's okay. But can you see the function that's being rotated around that metal thing?
It's like it's the top part.
Mm-hmm. Mm-hmm. And then that function, that top part, is being rotated around that axis, which is that piece of metal.
So to get a specific shape, would they have to put in a specific function?
Yes. Yes, they would.
No, that's actually pretty cool.
It is so cool. You know, one of Rome State's hottest programs right now is mechatronics. It's industrial robotics. Clinton High School kids are graduating high school with an associate's in mechatronics, just like you're going to graduate high school with an associate's, but their associates starts them out about $45 an hour.
Why is this going to start me off with like leaving? That's it.
All right. One last thing I found last night. What about a vertical lathe? This dude showed how to turn your drill press into a lathe.
How's it going today? I wanted to try and turn my drill press into a wood.
I couldn't find one,
I'm
but
doing
nobody's
something a little
talking.
bit different here because normally I tape these introductions.
Okay, watch this.
I could
Again,
then
a
chop the
block
wood up
of
into the
wood.
drill press. I used a 1/4-inch chisel to round out the
Think
blank
of
into a
his
cylinder.
chisel as being the function.
The tool rest didn't work too bad, but towards the top there was a little bit of flex.
The width of his
This is actually
screwdriver
only the
is the
second time
width
I've
of
ever
each
turned anything.
disc.
The first
The
one just
discs
being
are
a pen at a
stacking up
woodworking
vertically
shop.
rather than
Basically, I just took my
horizontally.
time. After a little bit, the dead center started making a squealing
And
noise.
rather than having a fully
quick shot of
automated
spray lubricant,
function
and the noise was
machine
gone.
that uses a function
Then
to
working up
determine
through
the
the
width
grits,
at
I
each
started out with
of
60
each
grit, 80 grit, 150, 220, and then I
Yes.
finished it off with, I
He's
think it's a
determining it with
320
his
grit foam
screwdriver.
pad.
and a piece of sandpaper.
It didn't turn out too bad. I could then just cut the ends off at the miter saw.
All right. So
The
you've
maple
seen a
blade got the
horizontal
same
lathe
treatment.
and a
Here I was getting
vertical
a little
lathe.
bit more daring though.
And it really did help me picture spinning discs. Those two videos did. All right. So we need to do a problem so that you can do some homework. Well, let's look at one in the book, and then we'll do just a few more, and then I'll give you some homework. Cheryl said, what about a trigonometric function? Well, example 1 is a trigonometric function. Let's play like we programmed that lathe to use the function square root of sine x, and here's the radius determined by that function. It would start out with skinny little or short little disc, and then your disc would get taller, and your disc would get taller, and your disc would get taller, and then all of a sudden they start getting shorter again. You have infinitely many discs in there. Each disc has a radius of square root of sine x at whatever x value you're talking about. So the radius is square root of sine x. Here's what that would look like if you spun it around the x-axis. My rectangles are perpendicular to the x-axis, moving from 0 to pi. So I integrate from 0 to pi of that radius squared. The integral symbol adds up infinitely many discs, the surface area of infinitely many discs, and times pi would give you the volume of that solid. Okay? All right. How many can we do? I'm just going to start carrying everything I own with me at once because it seems like I never have what I need. But I don't want to carry everything. I'm missing. Oh, no, it's on the back. It's on the back. I thought I had everything I needed. All right, so number 6. Number 6, graph torus. This little arrow shows that this volume is going to be generated by rotating that area around the x-axis. And you can see, if you look up at my pen, you can see that that would make a cone. Yeah, it would make a cone. It's spinning around the x-axis, so this would be the end, and it would come to a point up here, and it makes a pyramid in 2D. It makes a cone in 3D. So how do I find the volume of that pyramid or the volume of that cone? Pi times the integral from 0 to 1, because we're using horizontal rectangles. The lathe is moving from left to right. Lathes always move from left to right or from bottom to top. I don't know if that's true in mechanics, but in calculus it is. Integrate from 0 to 1. That function's height squared, negative x plus 1 squared, dx. Dx is the width of each cylinder, or the width of each coin, if you want to think of it as a coin. So hopefully that's what you wrote down. Pi times r squared dx. Okay. Now there's a whole different thing that we're definitely not going to talk about today, but you can be sleeping on it. What if this was spun around the x-axis, but it wasn't touching the x-axis? What would that be? Yes, we're going to talk about discs with holes in them tomorrow. Okay, what about this one? This one, the rotation is about the vertical axis. What does that tell you about the rectangles if you're rotating around the vertical axis? They're going to be horizontal. Think of your lathe starting at the bottom, going up. The volume would be given by pi times the integral from what to what? 0 to 4, and it's this 0 to 4, not this 0 to 4. 0 to 4 of what determines the height of each rectangle? The function, and we've got to square that for the area, the area of one of the discs. So pi times the integral from 0 to 4 of the radius squared. Now, the integration on these would take a while. That's why on the test you have some that just say set up the integral and don't evaluate. If they do evaluate, you can evaluate it on your calculator. You can give me a decimal approximation of this. There may be 1 or 2 problems like this test that I want an exact value just to make sure you don't forget how to integrate by hand. But most of them are going to be either just set it up so that I understand, or that I know that you understand how to set it up, or set it up and then punch it on the calculator. All right. What about number 3. I'm glad we got to this one. Number 3. No, it's my third example. It's not number 3. It is number 26. All I know is y equals 0 is the x-axis, and I hope I get some perfect credit for that.
You gotta find the intercepts.
I do have to find the intercepts. And how do I find the intercepts? Set that equal to 0. And I can just look at it and tell if I set that equal to 0, what would I get? 0 and 2 and negative 2. Now, if I want to know, I just want a quick graph or a quick mental image of what that looks like, how could I get it pretty quickly? Yeah, punch it on the calculator. Punch it on the calculator. It looks pretty much, it has intercepts at negative 2 and positive 2 and 0. From negative 2 to 0, it's below the x-axis like that. And from 0 to 2, it's above the x-axis like that.
Integrate from 0 to 2 and multiply it by 2.
Yes. Yes. But this takes care, this is the example that I wanted to show you. What if you have something below the x-axis? Well, when this is rotated, it's going to kind of be like a barbell. You're going to have that end, and you're going to have that end, and the two ends are symmetric. So maybe instead of pi r squared, we'll have what? 2 pi r squared. Then we would have to find the volume of each and then add it. We could do that. So the volume would be 2 pi times the integral from what to what? Yes. You don't want to go all the way from negative 2 to 2. If we did integrate from negative 2 to 2, what do you think that integral would be? 0, because there's just as much area below the x-axis as there is above the x-axis. So we only integrate from 0 to 2. What's the function that determines the radius of each of those coins or each of those discs? X times square root of 4 minus x squared. So that with a square outside is r squared. We're integrating with respect to x. Got it? Well, I can tell you because I wrote it down, but I don't want to take time to integrate that by hand. Yeah, it's 128 pi over 5.
Substitution. Is it x?
Uh-huh. If you let u be 4 minus x squared, then what would du be? Well, actually, when you squared that, it wouldn't have a radical anymore. That would just be a polynomial, and you could integrate it term by term. All right. My fourth example was number 28. And it said y equals 2 over x plus 1, bounded by the x-axis, the y-axis, and the line x equals 6. I might want to just make a note that when x equals 0, what is y? When x equals 0, y is 2. That's one of my ordered pairs I can graph. And when x equals 6, what is y? 2/7? Yeah, good luck plotting that. It's going to be not far from 0. So here's 0, 2, and then 6, and not much above 0. And I can punch it on the calculator, but I'm pretty sure that's going to be a smooth curve. There's a discontinuity at -1, but everything to the right of 0, that's just going to be a smooth curve with the y's getting smaller and smaller. So if I rotate that around the x-axis, y equals 0, rotating around the x-axis, do I have horizontal rectangles or vertical rectangles? Vertical rectangles. Here's all the discs that I'm adding up. The direction said, and I didn't read it, bounded by the graph, let's see, on the volume of the solid generated by revolving the region bounded by the graphs of the equations about the x-axis.
That's a lot.
Yeah, about the x-axis. So I'm going to draw the mirror image of that flipped over the x-axis, those same 2 points, and then the mirror image, and then put some ends on it, and there's my solid of revolution on the very best I can do. Not trumpet. Alright. So my volume would begin with what? Pi times the integral from
0 to 6.
0 to 6 of what?
2 x plus 1 all squared.
The radius squared dx. Where are we? That was example 4. Okay. Here's that note. I wanted to say about number 10, and I won't even go back and write it down. But number 10, this is the integral we set up, and I did it to get the exact value, 128 over 3 pi. And you told me that when I generated that, or when I spun that with respect to the y-axis, I'd get a hemisphere. And I have a formula for finding the volume of a sphere. It's 4/3 pi r cubed. That's exactly, you get the same area. If you say half of 4/3 pi r cubed is 2/3 pi r cubed, you get the same answer. All right, number 14. Says actually, it has 4 parts, and I want to do the, dang it. I want to do part D, but there's something I need to show you on the note. Okay, back to the notes. That's the notes I've already written down. There we go. Back to the notes a minute. We did 6, 10, 26, and 28. What if our function wasn't being rotated about an axis, but it was rotated about something else? Y equals 2 minus x squared, that's a parabola. We want to rotate it not about the x-axis, but about the line y equals 1. How could I find where that parabola touches the line y equals 1? Just set it equal to 1 and see what you get. Set 2 minus x squared equal to 1, and you would get x squared, or you get x equals -1 or +1, which gives us the 2 points, -1, 1, and +1, 1. So here's one piece, 1 point. Here's 1 point. We could also see that when we let x be 0, what would y be? 2. So there's my piece of parabola that I'm going to spin around and around, not the x-axis, but that line y equals 1. So, Miss Emma, this one doesn't have a hole in it because I'm spinning it around y equals 1, but if I spun it around the x-axis, it would have a hole in it, which we're not going to talk about today. So, let's see what difference that would make. If we're spinning around a horizontal axis, what does that tell us about the rectangles? They're vertical, perpendicular to the axis of revolution. So we're adding up all of these vertical rectangles. That means I want to integrate, well, pi times the integral from what to what? And I'm going to lathe moving this way. -1 to 1, because with vertical rectangles, everything is with respect to x. And there's going to be something dx. I'm going to write that down because I get partial credit for it. Because I have to figure out what to use as the radius of this thing. It's not just 2 minus x squared, because 2 minus x squared, and I don't even want to draw this in, but that would give us the radius all the way down to the x-axis. And this doesn't go all the way down to the x-axis. So,
Subtract.
+1. Remember top function minus bottom function? This is f of x, and this is the lower function. Just remember that volume is area times length, and the area is pi r squared, and the radius here is not the whole 2 minus x squared all the way down to 0, it's 2 minus x squared all the way down to 1. Squared, yes. So I could write that as pi times -1 to 1, negative x squared plus 1, or 1 minus x squared dx. All right. I wanted to do 3 more. We don't have time. What I was going to say about number 14 is it was going to be our first one that was rotated about something other than the x-axis. I just need to, if I'm integrating from left to right, or if my lathe is moving left to right, I need to integrate top minus bottom. If my lathe is moving from bottom to top, I need to integrate right minus left. Positive minus negative, right minus left. All right, look at some more examples in the book since I didn't get to do those 3. But go ahead and try that day 1 homework. And if you need to see one of them tomorrow, we'll do it. I'm not too old for anything. Have it, Miss Samantha? Okay.